Now in section 16.2, we're going to raise our difficulty level by looking at non-rectangular regions. We knew it was coming, and it's already here. Now remember that the volume is the double integral over the region of f of xy dA. Now, when it was a rectangle, the region was really easy to figure because you would have numbers in all four positions for both your x and your y. But it doesn't have to be a rectangle. It could be any region of any shape. So how do we set up the limits of integration? It depends on what that shape is. So it's important to note that the outermost integral must have constants. So the outermost integral has to have numbers on it, but the innermost integral does not. All right, so the volume would be equal to, all right, so let's work this from dy dx. Okay, so we're going to take the integral from a to b, and then we're going to take our function f of xy, and we're going to go with respect to y, then with respect to x. Okay, so the y values then need to be related to what they were on these curves. So this function, this bottom part right here, so this is the bottom, I'll just write bottom next to that. It's the lower value, right, the lower curve. So that means that down here I would have y1, which is g of x. And up here I have the top, right? So up here is the top function, which I'll call y2, which is h of x. So they don't have to be numbers for the inner integral symbols. The last two have to be numbers. So you're going to say, look, I'm going to go from this lower curve to this upper curve, so low to high. So this is the bottom of that approximating rectangle, and this is the top of that approximating rectangle. And then I'm going to take those rectangles and stack rectangles inside this from the left to the right. The left being A, right over here, right? X equals A to X equals B, which are those values. And notice those are constants. All right, what if I went the other way? What if I had functions in terms of y? Well, then I would do the derivative, or the integral, excuse me, with respect to x first. So I think about an approximating rectangle, and I'd say, all right, the volume is going to go, and then the constants are c here and d here. So this is y equals and y equals. So I'd be from c to d. Again, those are constants there. But the inner portion is not. So this inner portion is going from one function on the left to one function on the right. So this one is on the left, this is on the right. So the left-hand one is g of y. So I'm going to take my integral from x1, which is g of y, and then I'm going to take it to x2, which is h of y. This is the right, and this is the left of that approximating rectangle. And then I'm going to stack the rectangles from c to d. So have my function f of xy, and then I'm going to say dx, dy. All right, that's the theory. Let's see how it works in practice. So for each of the following examples, evaluate the double integral over the given region R. And there were no given regions, so let me put them in here for you. So this particular one is going to have the region right here. So region R is going to be right there. So that'll be RR. All right, let's work with that one just for starters, and then we'll go to the other one. Okay, so for this one, let's think. I want to find the volume. So I need a double integral. And then I want to think about my function, right? So that's xy. So it says it right here. You can see it right there. That's your f of xy right there inside. So it's going to be xy. Now, which way do we want to go? This particular one, we could actually kind of go either way. I'm going to go with a vertical rectangle approximation, which lets me know that I'm going to be stacking from low to high, and then dx is my secondary, right? So I'm going to be going dy, then dx. All right, so x is easy because x has to be constants. So we're going to take x from 0 to 2. No problem. Easy peasy. The harder part is the y values. So we need to go from the bottom to the top. And we can't put numbers in because, of course, it's varying over time. Sometimes it's a longer rectangle than a shorter rectangle. So the bottom is actually always the x-axis. So that would be y equals 0. Sorry, y equals 0. Right, the x-axis, right, is y equals 0. The top part, well, this is a parabola, right? So this is y equals 4 take away x squared. All right, so that's what we're going to put in here. 0 to 4 minus x squared. And these are y values, right, because they go with the dy. And now we have the setup. From here on, we just need to integrate. So we want to integrate, and you can't just reverse them. You can with rectangular regions because it doesn't matter, but with a curve like this, it matters, right? You can't reverse them because this last one has to be the constants, which in my case is my x values. So I'm going to have to integrate this with respect to y. So that would be 1/2 y squared times x. So 1/2 xy squared. I'm going to take that from y equals 0 to y equals 4 minus x squared. And I still haven't integrated with respect to x, so dx just kind of sits there. So this is the integral from 0 to 2. The 1/2 actually I'm just going to bring out in front because just like with Calc 1 and Calc 2, when you have a constant multiplied in an integrand like that, it's just easier to pull it out. So then I'm going to take it x times, and then it would be 4 minus x squared minus x times, well, 0. Right? So that's not going to matter in the back. Right? This is just going to be 0. So we're not worried about that. So that means I'm integrating 1/2 times the integral from 0 to 2 of x times 4 minus x squared with respect to x. And we're just going to make Maple do that last bit. We just make a note that we used Maple, and we're going to come up with an answer, which is 16/3, or approximately, well, not even approximately, it's exactly 5.3 repeating. All right, let me show you that in Maple. All right, here's my surface. You can see that it looks like this. This is what xy looks like. And I also plotted 0, which is the xy plane, because this is plot 3D. So 0 got that gray piece in there, so I colored it gray. And then x times y is actually colored x times y, which is kind of cool. So this surface, this rainbow surface, that's what we're finding the volume of, right, if you will, between that rainbow surface and the xy plane. And I'm graphing it, and you can see that that is not a rectangle, right? That's actually a parabola. Let me flip it around. You can see it a little bit. There we go. I got it into place. So there's the y-axis, there's the x-axis. Now, they look like they're the same length, but that's because the scaling is not constrained again. So that's that parabola that we're looking at in the first quadrant. And so there we have it. It's 16/3, right there. Isn't it beautiful? Now for the second piece, again, we didn't have a region given, so I'm actually going to do the whole thing because I want you to see what's going to happen here. Okay, so this will be my entire region, R, right there. Okay, and again, I can do dy dx. There's nothing stopping me. I mean, I can set this up the same way I did the previous one. Don't worry, we'll have some dx dy examples. Don't fret. Okay, so volume is equal to, but now I'm going to go from -2 to 2. Instead of from just 0 to 2, I'm going to go from all the way on the left to all the way on the right. And then it'll be the integral still is from bottom, right? The bottom is y equals 0 to the top, which is y equals 4 minus x squared. So I'm still going to go from 0 to 4 minus x squared here. And then it's xy, and then it's dy dx. All right. So just like before, right, this is no problem. So from negative 2 to 2, and then this would be 1/2 xy squared from y equals 0 to y equals 4 minus x squared dx. Okay, so we already know where this is going to go. This is going to be 1/2 negative 2 to 2 of x times 4 minus x squared squared dx. But let's look at what that is. All right, so here it is, and I actually found it right there. It's 0. Now, how in the world? It's because, look at it right here. This is what it looks like. So when you have the one piece that's positive, right, that we already found, that was 16/3, but then on the other side, there's an exact companion that would be negative, right? I actually have it kind of turned around. It's supposed to look like this, right? So there's the piece we found already there sitting up on top, but there's its exact companion on the bottom. And so what happens is they cancel each other out. Right? The positive and the negative volumes cancel, and we end up with 0. So this is 0. We'll make a little diagram for ourselves real quick. So we had kind of a positive component and a negative component, right? The positive piece was over here, was positive 16/3, as a matter of fact. And then I'm obviously drawing this two-dimensionally when it's an actually three-dimensional thing, but you get the idea. So this was negative 16/3. And so when you add them all up, the integral of the entire thing was 0. So it's kind of interesting to see how that can happen with a three-dimensional object like that. And it's the same thing as when we were doing two-dimensional objects. If this was two-dimensional in Calc 1, that would also have been 0 for an area for the same reasons. It's the difference between distance and displacement that we learned about in Calc 2, coming to rear its head again, but now in 3 dimensions.